welcome everyone to the second part of this year's QTX. As Alex pointed out in the beginning, this conference is a sort of a brainchild of us starting with joint collaborations, focusing around technology development for cold atom experiments on nanosatellites. And no surprise, the second session will then more focus now on these enabling technologies in part, but also on designs of actual cold atom systems to be operated on a nanosatellite, and will end with a little bit of a bigger satellite called the International Space Station. I'm especially eager to hear from Dave how it is in these times at when home office is something we all have to face, how you operate the ISS or running BC experiments on it. But let us start with Aaron Strangfeld. He's actually one of my students who was working during his master thesis with Alex Ling in Singapore, and also with Ravi Kumar jointly on developing a small and compact optical frequency reference. And he will show us about the outcomes of his thesis right now. So Aaron, please start.
Thank you very much for the introduction, Markus. So as Markus already said, I'm also a member of the Joint Lab Integrated Quantum Sensors, also as the presenting speaker, Mustafa. And just to introduce the focus of our work again, so we are working on miniaturizing quantum technology until the chip level in the long run. And on the next slide, you can see the fields of research in our group, ranging from devices on a spectroscopy of thermal gases, or to interferometry methods, hybrid integrated systems, but also cold atoms systems itself. And the work that I'm going to present is embedded in the first section in the upper left. So I will talk about the development of an optical frequency reference based on rubidium that we are aiming to be compatible for the CubeSat platform. And in this, we collaborated with Alexander Ling's group at the CQT. And for the development, the design, and the assembly of the module itself that you can see on the right here, we also were in tight collaboration with another joint lab at the FBH, Joint Lab Quantum Photonic Components, led by Andreas Wicht. First, I want to motivate why we develop such compact systems. And one example I want to point out, which is the EDGE atomic experiment for dark matter and gravity exploration in space. So in this white paper recently, it was said that atom interferometers, so one type of quantum sensors, can be used to measure gravitational waves and do research on ultralight dark matter if operated in space. So as the development and the technology of quantum science is going on, we are still kind of early on the technological side. So what we will need to have low risk missions with high costs is technology development and increase of. So we need increase of the technology readiness level for these space missions. And one option to do this, it was already introduced by Daniel Oy, is using CubeSats. So using CubeSats beyond various applications in science and also on the commercial side, we are interested in the technology demonstration of quantum technology. And by this, we want to make use of all these benefits, making higher risk missions possible because of low launch costs, building less complex systems and having them in orbit, and having an iterative development, a rapid prototyping phase during the development of these technologies. There is a big but, however. We have extreme swap constraints. We need to be small, we need to have low power consumption and low weight. And before I get into the process of developing a technology for the platform and for quantum technologies, I want to give a brief introduction about the principle of optical frequency references. So optical frequency references are based on lasers that emit light at a specific frequency. And if you put some absorbing matter in the path of the light beam, and detect a signal on a detector, you can see a spectrum by varying the frequency, with a dip if you hit an absorption line of this medium. And by some spectroscopy method, you can then translate this Lorentzian dip into an error signal. And by using this error signal and the zero transition through the absorption line center frequency, you can stabilize the laser. And then there it is, the frequency reference, a stabilized laser to an atomic transition. To evaluate the stability, to evaluate the performance of such a frequency reference, you use the Allen deviation. So this is an equation to estimate the Allen deviation, which is a statistical measure of the frequency deviations. And I want to emphasize one term in this, which is the slope of the error signal at the center frequency. And as you can see, if you want to reach low frequency deviations, low Allen deviations, we will need to have a high slope. So what you want to achieve is really narrow lines, really narrow absorption lines that translate to a high slope of the error signal. So everything that broadens your absorption line is bad for your stability. And just to give an impression what kind of performance, just to have a benchmark for cold atom systems, you can estimate the stability for rubidium applications that you need Allen deviations lower than 10 to the power of minus 10. The open question on the physics side is how do we place this absorbing matter into the beam path, and how do we prepare it to have really narrow lines? And there are different options, and I will give you a simplified overview here, which starts with the highest performance systems being lattice clocks. There are also other systems that have high performance like ion clocks, just to be simple here. These lattice clocks have the highest performance that has been shown, but also have the highest complexity and thus the highest swap requirements. Medium performance systems that are also developed in our lab are clocks or frequency references based on atomic beams. And the simplest systems, but also with the lowest performance, are vapor cell based systems. So warm vapors just encased in a glass cell. And here, just to give you an overview about the range of Allen deviations that are achievable with these optical frequency references. And as you can see, of course, we are striving for the CubeSat. We want to use the simplest system possible as long as it gives us the necessary performance, which are vapor-based systems. And we already, in our group, we already gathered some experience about this. We have launched multiple missions with a payload being an optical frequency reference on sounding rockets. So here you can see an overview from launch day. It's ranging from 2015 to 2018. The most recent one being a iodine-based payload. You can also see from left to right, the performance is increasing, but also the swap budget that is necessary. So the closest thing that we have done to CubeSats is actually the focus payload on the left. So the goal in designing such a system for CubeSat was to start there and trying to get it small and trying to reduce the power that it needs. And with this, I came up with a design which is quite straightforward regarding to the alignment and is fiber coupled and already promising. The length is limited to 65 millimeters based on the 100 millimeter side length of a 1-unit CubeSat system. So I would go through this quickly just to explain you how this optical setup works. So I will start in the center here at number 10 with a DFB laser diode. So the light from this DFB laser diode is collimated on both sides with a pair of collimating lenses. And then the diode is protected from back reflections by 2 optical isolators. The front port is then the major output coupled to a polarization maintaining fiber here. We need some space for the fiber bending, as I said. That's why it's not 100 millimeters. On the rear side, there's the spectroscopy unit. So instead of just using, as you remember from the scheme at the beginning, shining the light through the vapor cell and detecting it at the end here, we use saturation absorption spectroscopy. So this spectroscopy method allows to have performances 2 orders higher than if you would just shine the light through the vapor cell, because we can reduce the effect of Doppler broadening because this is a warm vapor. So light is shining through this vapor cell, gets reflected at the mirror, and as there is a quarter wave plate 2 passed in between, we rotate the returning light, the polarization of the returning light, and it can be deflected by a polarization beam splitter and then focused on a fast photodiode. So there is still one major issue with this design that had to be addressed. The rear optical isolator is quite close to the vapor cell. So what? The problem is that the magnetic field that we're using really narrow lines and lines in the hyperfine structure of rubidium get affected by magnetic fields through Siemens splitting. So if we have a magnetic field close by, this will broaden our line, and as you remember, this will deteriorate our performance. And for this purpose, I did simulations about the effect. So you can see in the upper graph here, indicated by A, the magnetic field strength of the optical isolator dependent on the distance on the x-axis. And based on this, I use the open source software Alexus to simulate the effect on the spectrum based on this magnetic field. And the resulting spectrum, I fitted a Lorentzian to and estimated the slope by dividing the amplitude by the width. And the results of the simulation you can see in the lower 2 graphs. So first, I evaluated how far do we have to put the vapor cell away that we get an acceptable decrease in the performance. We used a 50mm cell in this simulation. And as you can see, as it's line width dependent first, so depending on your line width, narrow lines get more affected. And on the other hand, distances at about 10 to 20 millimeters are enough to reduce the effect significantly. In the right graph, you can see an evaluation of the cell length. So maybe intuitively you would think, okay, maximize the cell length because then you have the maximum of absorption. However, because of the effect of the isolator's magnetic field, by increasing the length and thus increasing the path length in the magnetic field of the vapor, you actually get an optimum length. As we estimate through different broadening effects, we estimate the line width to 20 megahertz. Which shows an optimum cell length of 50 millimeter, which settled this issue. As you can see, for the green line with 20 megahertz, there is still some loss. So we lose about 25% at a distance of 10 millimeters, which was the final distance. And after this was settled and deemed sufficient, we could go on to the mechanical and optics and the mechanical and the electrical design. So here you can see how the whole module is set up. You see the linear design of the optics in the left image, and the optics are mounted on benches, and these benches are connected to a single Peltier. So this gives us the chance to reduce the number of temperature controllers to 1 if you wanted to heat the vapor cell independently. In the center, you can see how a detector board and an interface board are connected to allow for coax connectors. And on the right image, you can see the encasing of the module by aluminum walls and an acrylic glass lid for presentation purposes. The resulting module after assembly has a swap budget of 35 cubic centimeters in volume, 73 grams in weight, and a power consumption of 780 milliwatts. You can see the €1 coin just as a size comparison. The total module with the encasing has a length of 70 millimeters. After this, I went on to the performance evaluation. We wanted to know, does it still keep up with performances shown in the bigger modules? And for this, I did a 3-corner head measurement. So by using 3 references and assuming that the noise contributions of all references are uncorrelated, you can use 3 comparison measurements by beat nodes to evaluate the individual performance of the module. We called it iCube for integrated quantum sensors on a CubeSat. On the right, you can see the measurement results. So the blue line indicates the performance of iCube, while the slightly transparent lines are the performances of the references. So the first thing that you can see is we are well below the limitation of 10 to the power of minus 10. So performance holds true. But even more impressive is that we achieved to have similar performance to the much bigger systems that we compared to. So this is quite a success. I put also another graph below, so showing the time-dependent Ln deviation, or the Ln deviation depending on the averaging time, in the comparison to a two-photon reference. So two-photon spectroscopy of rubidium is a high potential scheme for compact optical clocks. So these people strive actually for even higher performance, and activities to realize systems like this are also ongoing in our group. And you can see there are some, we are above the performance, so we have lower performance in the two-photon reference, but still we are in reach, which is quite good. For these people in the audience that know how to read these Ln deviation graphs, I want to point out on two features that you can see. So you would expect something like the green line in the upper graph here. However, you can see this pronounced bump, and you can also see this increase in the end. So the bump is actually subject to further investigation. So we need to consider, is it temperature fluctuations at the vapor cell, or is it something on the electronics side, on the stabilization side? So this is still work to do. And in the end, you can also see this rising of the instability again. We didn't put much effort yet into encapsulating this module in a proper way and saving it from ambient temperature fluctuations. So this will be investigated also, and we will see if we can improve on this. To give a more context to the introduction, we started with saying that I started with saying that the focus module was like the starting point, and actually the focus module is ref 1 in this system here. And just to give you a comparison, so this is the focus module, and there's the iCube module. And so we achieved a size reduction by a factor of 50 by maintaining the performance. From there, you could start to continue on this prototyping development phase, making this thing hermetically sealed. And after this, you could think of experiments. So first you could verify the operability of the frequency reference on a CubeSat by building two identical references and verify the performance by a beat node between those two. Alternatively, we could go on further. We will hear about a system that is doing this. Code atoms on CubeSats. So this is just an impression how this could look like in a 3-unit CubeSat, just a simple scheme. But by further reducing the subsystems that are needed for code atom experiments, this is actually in reach. And we could also show that the iCube optical frequency reference is suitable for driving code atom experiments. So here you can see a loading curve of a magneto-optical trap, where the laser system is referenced to iCube. On the right, you can see the fluorescence of the particles in there. And finally, so this is work ongoing. We are working on how a complete CubeSat payload could look like. And this is the current status. So what you could do is take the frequency reference, of course, then you have some system for modulation, demodulation, and PID. So the first two tasks are related to our spectroscopy method, frequency modulation spectroscopy. You have one current temperature controller. You will need to design a custom current driver. In this, we are closely cooperating with Alex Ling's group at the Center for Quantum Technologies. And then there's iCube. And such a payload occupies 0.6 units of a CubeSat. Finally, I want to thank all the collaborators and supporters during this project. Ravi Kumar was already mentioned, Alex Ling, Markus Krutzik. I don't want to count them all, but they were all super important for this project. And also thanks for funding from the Berlin University Alliance in this project. And on my last slide, if you have questions, of course, ask them after the other talks. But also get in touch with us with QT Berlin. So this is our networking initiative in Berlin. Talk about quantum technology, prospects for industry, but also research. So we would be happy to answer questions and get in touch with you. So thank you very much.
Okay, yeah, thank you, Aaron, for this presentation. And as it has been done before, we will collect all of our questions for the Q&A later on. I'm handing over to the next speaker, which is Mike Holynski. So Mike is a senior lecturer in Birmingham and an expert in atom interferometry on also many like unusual platforms out of the laboratory. And yeah, we also share some joint proposal ideas, and I'm happy to hear his presentation. Mike, are you there?
I am here, yes. Hello.
Hey.
Shall I begin?
Yes, please.
Okay, great. Let me just share on screen. While it's loading up, just apologies that I have several children in the house and they're being rather noisy. So if you hear any background noise, apologies for that. Good morning, everyone. And thanks very much for the invitation to speak here. It's really humbling, actually, to have the opportunity to speak amongst some really fantastic experiments. I remember when I was doing my PhD, which I don't know how long ago that is now, people were very focused on things like the Qantas experiments and demonstrations of microgravity BECs in the first instance. And back then, me and one of my colleagues were talking, and we said, well, they said to me that they never thought you'd see a BEC in space in any capacity. They didn't really believe the trajectory. And I said to them that actually, you know, of course it's going to happen. And one day we'll also have BECs in watches, or at least watch-sized packages. And for those of you, I guess there may be some people who are a bit earlier in their career. For those of you who haven't seen these things coming, you know, just to say, the results we're hearing about today are really fantastic stuff. So hearing about Bose-Einstein condensations in space is really a major breakthrough. It's really a great thing to hear. So anyway, with that preamble, I'm not going to say anything quite as exciting as that, I'm afraid. What I'm going to talk about, I've been invited to talk about today, is our project CASPA, which is actually really about how can we progress things towards much smaller platforms, as Markus mentioned. So I'll give a little introduction to what we do. We're very focused on quantum sensing with cold atoms at Birmingham. What you can see here, just to give a little picture for people, this is a magnetoptical trap of rubidium. This is around 10 to the 9 atoms. Some laser light comes in from every direction and cools the cloud. There's also some magnetic fields that we use to actually provide a spatial component to that force. You can just about see those here. And on the right-hand side here, we have the same technology, but now this is for strontium, which is underpinning different types of sensors, typically. So here, this is rubidium, typically used for atom interferometry. It's pretty much the workhorse for atom interferometry. And on the right-hand side, we have strontium, one of the typical candidates for optical clocks. Of course, you see clocks based on rubidium, RF clocks based on rubidium. You also see atom interferometry with strontium, but that's the typical breakdown. So atom interferometry, which is my main background, just to give a short summary, what you can think of is if we imagine an optical interferometer, we take two waves, we split them with a beam splitter. You can see my little beam splitter here. We let the two waves propagate on two different paths, and we push them back together with mirrors, recombine them on a beam splitter. And I guess people are mostly confident with this. What happens when we look at the output of those two ports on the beam splitter is if we change the path length difference between those two trajectories, we see a change in phase and change in constructive or destructive interference on the outputs. We can actually do really the same thing with atoms now. So here, what you can see, this is in the picture, a two-level atom. We start with all the atoms in the ground state, for example. We wait some time. We apply a pulse of light that's given the right amount of time with the right detuning and frequency, such that the atoms have a 50% chance of absorbing some momentum from the light. And if we bring the light in the right way and we do things as we want, we can then deliver a 50% kick to the atoms such that half of them, well, half of their probability distribution will start moving apart from the other. So some fraction receives a kick and some doesn't. And if we wait some time, they'll spatially separate these two momentum states. And just like in the optical interferometer, we can then apply another pulse of light, which inverts that population distribution, which then also flips the direction of the kick. And waiting some time again, we can apply a final pulse, which merges those trajectories again and look at the outputs. And now what we can see is over here, this is millivolts on a photodiode, but looking at the fluorescence from one of these two atomic states, rather than measuring light from an optical interferometer. And here we see, by changing the phase between these two paths, we can see a fringe. And this is something from one of our experiments I sent some years ago. What's quite interesting about that is that actually now, if we have these two trajectories and we imagine having, for example, some mass down here moving past, that mass will create a slightly different force or pull on the two trajectories, which creates a phase shift on the outputs. And that's something that people have actually measured, and means we can use atom interferometry for things like detection of gravity. So you can do that, and this is an example of one of our gravity gradiometers at Birmingham. I won't talk too much about this. Here we have actually two atom interferometers on top of each other. So there's one up here and one down here. Over here, this is the correlation of those two fringes from those. Don't need to worry too much about that. But with a device like this, we can take that outside. We can measure small changes in mass, and people start to make these things kind of commercially now. And you see companies like Muquans and AOSense really building commercial atom interferometers. This version is quite large. You know, it's a large washing machine, and we have a sensor head here that's about 100 kilograms. But we can start thinking, actually, what use may this have in space, and why might we want to do that? Now, in space, gravity mapping actually is very interesting. It has a wide range of applications. This is a beautiful picture some of our third-year students made. And what you can see is, as you add increasing sensitivity, you start to see more features of the Earth, for example. So at very low sensitivity, you're just going to see the shape of the Earth. As you start to add more, you'll start to see things like the course geography. And then when you're really starting to get to good performance, you'll start to see major geographic features, tides, internal structure. But if you really get very far, you'll start to see actually fine features in geography, and also water and ice distribution. And this is a really interesting thing. And if we look at some of the experiments that have operated in space to date, so Gochi and Grace, for example, these experiments have already had real major impact on people. So with Grace, they managed to detect draining of water in aquifers, I think in India, but maybe Africa as well. And with that, they could see actually the way water was being used in the country maybe wasn't quite the optimal way at that time, and provide some advice. So if we can actually start thinking about where quantum sensing may complement, there may be new parts of this diagram that we can start to fill in. It's one thing is just actually, can we improve the resolution? Now, doing that is very tough. Sorry, the spatial resolution, doing that is very tough. You need a more sensitive sensor, but also it can't be one that needs a very long time to integrate, because these spacecraft move pretty fast. I think 7 kilometers a second or something like that, which means if we, one concept for cold atoms is we do this atom interferometer, and in between the pulses, we wait for a very long time. And that long time means our space-time area, this kind of area of the interferometer, gets larger and we get more sensitive. But if we do that for too long, then the spatial resolution will drop anyway, because we're sweeping out a large cone in space. So there are concepts, and people are thinking about how can we push in this direction along this graph and open up new applications from space. But the other direction one can think about is also how can we improve the temporal resolution. And ways to do that would be, for example, different orbits, or having more satellites perhaps. And I'm sure there are other concepts there too. And if you can start to do that, these are some of the projections from Grace here, sorry, I haven't got them for Gochi on here. They start pushing into actually movement of ice. And if we improve the sensitivity or the spatial resolution, sorry, also starting to look at hydrology. And this is where things get really very important. And I'm not going to say we've got an answer to this, but we're coming in to try and actually think, you know, how can we try and move into these kind of spaces? If you can start hitting these, you start dealing with problems like flooding. And that's a major problem for a lot of people in the world every day. So why should we not want to put cold atoms in space? And the main reasons are the technology readiness is or has been low in the past, and this has changed drastically in the last few years. But also, it's expensive to launch large and heavy things. And in concepts we worked on for ESA, looking at actually how can we make very sensitive systems, one of the problems is you need things like magnetic shielding for atom interferometry, and this creates huge weights and quite large volumes, depending on how you implement it. But in a kind of basic scheme, it becomes very, very difficult to get something that's even launchable. So this makes things very expensive, and therefore, since the technology readiness is deemed low, and large and heavy things mean it's expensive to launch, it's overall not a promising prospect for some of the space agencies, because they have to take a big risk and it's very expensive to do so. But, you know, as we've said, times are changing. We have things like Becquerel, the Cold Atom Lab, MAIUS. These have all shown actually there is a trajectory where the technology readiness is improving. And now we can say actually cold atoms are working in space. So the game is changing, and we can start to think, okay, what can we do maybe on the atom interferometry side there? So one thing we're quite interested in is how can we maybe start looking at this temporal problem by starting to contribute small satellites and pushing for much lower size, weight and power and cost of the overall system. And the cost there would also include the mission cost and that, therefore the launch costs. So by going to something smaller, maybe we can go to a more ubiquitous sensing scheme, for example, where we have, rather than 1 or 2 satellites, a swarm. And that may help with some of these temporal problems. So to do this, the kind of way we engage with this is we've been working for a long time with a partner called Teledyne E2B, who some of you may be familiar with. They have a lot of heritage in space. And one of their famous achievements is that they made all of the cameras for the Rosetta mission. But that's just one. You know, they're very strongly engaged in imaging for space, and actually a lot of your cameras, if you're working in cold atoms, may contain imaging chips from them. So we've started working with them on the exploitation of gravity gradiometers, and you can see this is a version of ours, and this is a version they've built based on that. They're now building the second iteration of this. This has some very promising applications in infrastructure monitoring, productivity and civil engineering, and some others. But actually, if we can start thinking about space as well, this really ties into, for example, their core business, and we may be able to use some of their expertise to help shrink things down. So, you know, based on this, we formed the CASPA consortium, and we have Teledyne there, but also we pulled in some expertise from across the UK. So we have XCAM, who are a bunch of people in Northampton who really specialise in cameras for space and the electronics around cameras for space. We have Clyde Space, who are a leading manufacturer of cubesats, and this is a concept diagram of one of their cubesats. Gooch and Hausco, who many of you will know, a photonics company. They've taken the lead on the laser system. Covision, they make frequency doublers, and they've actually been involved in the frequency conversion in CASPA, and that's very linked with Southampton. This is all funded by Innovate UK, which is a funding body in the UK for industry engagement. And here, this project's really been about starting to bring some of the UK industry knowledge into the picture. The goals that we set ourselves were, how can we, from the UK perspective, do something that can complement the overall picture in cold atoms for space by trying to get something that can be more easily launched. And, you know, this message goes back, this program started maybe 4 years ago, so that was before we saw some of the great successes in the programs you're hearing about today. And what we thought then was, well, it's quite frustrating actually, because you can see cold atoms technology is extremely advanced. We have some great stuff going on in the Qantas missions. If we can just put something, anything into space, even if it's quite cheap, if it can just demonstrate something that will really help, you know, organizations like ESA see this is starting to be very promising. But, you know, we understand the need for those agencies to have some confidence. But as I said before, another major aim is actually how can we reduce the swap? And as we set for our students, having a very rigid platform means there's no escape from meeting those swap requirements. So originally we looked at the kind of portfolio of CubeSats that are available, and they could go up to 4U. We managed to push them a little bit up to 6U. So that's a 10 by 20 by 30 centimeter box CubeSat. And that sets our overall envelope. So we had to think of a concept for, actually what's the sense in this if we want to ultimately get towards doing gravity gradiometry. So we looked to what we're doing in the hub there as our kind of first initial concept. This is the gravity gradiometer we're building now, and this is its kind of current status. So we have a laser system here. This is all based on telecom frequency double stuff. I can say more about that if people like in the questions. This is the main sensor head. It's all inside this magnetic shield. And this is all the microwave and control electronics. Total size is about 100 litres now, weighs slightly less than 17 kilograms, which is a bit over spec. It's meant to be 15, and it's a bit under 150 watts. At the moment, we still have to prove this concept. So it's currently just working on atom optics. It's got its first Rabi oscillations there. So this first beam splitter pulse has been implemented now. And we're targeting actually reaching some quite interesting performance. And because we know we can hit this kind of form factor, size, weight, and power, at Birmingham, we thought actually there's a good concept here for pushing things forward in CASPA. So we brought in, I've already said a bit about the partners, so I won't say too much, but I'll talk a little bit over the design. This is the overall payload design for CASPA. So we have here the main physics package, and I'll talk about the technology choices there in a moment. This is the telescope here. There's a fiber which isn't easily seen on the diagram, but it comes round to here. This is connected to the laser system, which is this pinky purpley box here. That's interfaced with these payload electronics, which do all of the control. These are built by XCAM. And that all fits into this, this overall kind of spacecraft structure, where 2U of the 6U is taken up by the platform avionics from Clyde Space. Now, the two kind of main technology choices behind CASPA, and they're not necessarily the best long-term choices, just to throw that caveat in, but they're what we thought we should do as our first step, are using prism MOTS and using telecom laser systems. So you can see here two examples from us. These aren't the ones from the references, sorry, but these are just some papers you can look at if you're interested. This here is a telecom laser we've built for our gradiometer. And what you can see is that it's quite compact. We have a 1U box here that can do nearly all the functions that we need for the system, and certainly for the CASPA concept. Now, most of these things are commercial off-the-shelf components. They're not things we build at Birmingham. That's not a capability we have, which is one of the driving reasons we've chosen to go with telecom lasers in the project. But the nice thing about the telecom lasers is it's all fiber integrated at this stage. And for us to do a first step with CASPA, which has to go through vibration testing and such, it's something where we can rely on the telecom industry specification without us having to do engineering on the optics, for example. And the second trade-off, or technology choice, sorry, was around how we actually generate the cloud. And here what we've used is a prism MOT. You can see an example here. We have 4 mirrors here aligned such that when we shine a beam of light from the top, these bring in all the beams from the sides, and with another beam coming from the bottom, we then have a 6-way cross of laser beams that create the confining force. Now, these actually have some good synergy, because one of the real problems that you have with telecom lasers is that actually, although everything's nicely stable because it's in fiber, it's very subject to polarization changes because of the vibration or thermal changes in the environment. The prism MOT synergizes with that quite well, because now we have one incoming beam, which means if we have a change in polarization, which we can project onto intensity, it's at least common mode, as in it's in every beam, so we don't see central movement of the MOT position, for example. So with this one, we see drift of the cloud center to maybe 1/10 of the cloud diameter, whereas with a 6-beam MOT, that's much harder to achieve with a telecom laser. And of course, the long-term trajectory would almost certainly be actually how can we move towards the kind of things you've been hearing about in the previous talks, shrinking down to micro on-chip systems, for example. But that's not something we can do in-house. This is the, I'm sorry, the reason I'm showing you these pictures is because I'm not sure that I can actually show the industry developments here, sorry, but they're based on these and they look very similar. So this is the main physics package with a biro pen for scale. You can see here the coils. This inside here would be the prism MOT, and we have a telescope coming here. It's a titanium chamber with an integrated ion pump inside and dispenser inside. And there's also some magnetic shielding not shown, which would just come around the outside here. These are all made with space materials, and it's been designed in particular to survive launch shocks and vibration conditions. We've tested the vibration. I'm not sure if they've tested the launch shock. I think at one point I deliberately dropped it on the table just to check that a bit. This is the engineering model, and what's really a nice thing for me is to see something that comes from, you know, the CAD design to really looking nearly indistinguishable in the picture. It's upside down here. What you can see is we have the main trap, telescope, there's the fiber coming around here, laser system, and this is now black box, much nicer color, and the electronics here. The only difference is the space avionics aren't real. They're just representative masses to give us the same mass distribution. That's been loaded then into this, this enclosure here and subjected to vibration testing. It's all passed that very well. The only issue they had is that one of the power lines, I'm not sure exactly which one, but something in this electronics board here, one of the incoming lines failed during the test, but that's now been, I'm told, rectified. So hopefully it would survive retesting. And to give you an idea of what's been achieved there, so the payload specifications, the target for the payload, not the overall platform, is 4U, so that's the cold amp part, so to speak. That's been achieved. The weight, they've managed to be slightly under budget there, so 3.5 kilograms or so, and they've managed to achieve overall 25 watts inside the overall power consumption. So you know that this is I think quite a nice achievement. And here you can see one of CASPA's rubidium clouds. They have put the number 10 to the 7 here, but I'm a little bit skeptical about that because it looks quite small to me. So I've removed the 10 to the 7, but I am certain that it's a rubidium cloud. It does look like it's a reasonable number of atoms for the laser power that we have. So sorry, it's not the laser power, it's the total power, but it's a reasonable number of atoms for the laser power that they have there, I would say. Now, one thing, of course, is, you know, if you're from the cold atoms background, you'll know this isn't the sensor. This is only part of the story. And in fact, it's not even a cloud at the required performance for being a sensor. So here we have, you know, maybe we have 10 to the 6, 10 to the 7 atoms, but they're at around 150 microkelvin. Really, for our first generation concept, we need that to be more like a microkelvin, which would mean some additional cooling steps, laser cooling steps involved. And ultimately, we're probably wanting to go to not BEC, but BEC temperatures, so that we can have much less thermal expansion and dephasing in our interferometer. Now, that's one side of it, but the other is that the laser system is very simple. It doesn't have any of the frequency control or power control that it would need in order to actually do interferometry or these next steps of cooling. So these are our two kind of main next steps. How can we get colder, and how can we integrate some kind of capability to do sensing? Unfortunately, we actually have the follow-on project funded now. So this is funded by the Centre of Earth Observation. I'm not really sure exactly what that is, but it's a kind of agency that sits outside the UK Space Agency in the UK. That actually starts on Sunday this weekend. So, you know, the world will change that day somehow or another. The consortium is a little bit different now. So we're still very engaged with the CASPA consortium. But as I say, the next steps are a little bit different. And so it's us and Teledyne again, but we've also brought in RAL Space, because one of the big things we want to do is actually move towards BEC type temperatures. So there we've brought in RAL Space, who have some heritage in atom chips, and you know we've worked with them in some ESA projects there, linked quite strongly to Hanover, who you know provide a lot of expertise on those kind of things. So here the first step is actually developing a physics package that's equivalent to CASPA, but now based on an atom chip. And we're still thinking, okay, is that still going to be a prism MOT as well? Because you can, before you go into the atom chip, you can have different ways you deliver the optical beams, but maybe also grating MOT, or maybe a 4-beam MOT. It's just when we start going to 4-beam, I find it a little bit difficult to conceptualize exactly how we keep inside the payload volume. Whereas on our side at UOB, you know, we'll be helping them to kind of think about actually how do we build this in a good concept. But we're also making an atom interferometry capable laser and demonstrating that we can do atom interferometry in a 12U type form factor. Not with, it won't be integrated into a 12U box in this step. That's where we want to go to next. And that's ultimately our goal. You know, how can we get something in the first generation that's a 12U CubeSat or so, something that you could launch several of these in a single launch and put them into an orbit where we then have, you know, a swarm of satellites or so. And of course, you know, this step might be something where in future that can be shrunk down through using some of the more exciting laser techniques that you're hearing about today. Now, that's nearly it for me. But mainly, I want to say thanks to some of the team. So actually, the people who really led the CASPA work at Birmingham are Jonathan Winch and Raffaele Nolli. Jonathan's a technician with us, formerly a student, and Raffaele's a postdoc. And they're the ones that really actually implemented all of the CASPA stuff. So although the results may look quite simple, you know, there's a main sort of trap here. It has to be fully automated, and all of the sequencing inside this avionics board has to be programmed such that it has a full startup sequence where the payload actually knows how to take care of itself and run in principle for 2 years without being touched. And defining all the protocols of how the laser gets itself locked, getting that to work, how the MOT images itself and such, has been actually quite an interesting thing for them. So here, actually, the laser lock, one thing to say, the laser lock is based on many-filter trap to save space. And, you know, how you go through the sequence of acquiring that is quite an interesting one. And yes, and, you know, thanks again to our partners. This is the overall team. You know, as Markus mentioned, we work on some of the stuff, and these are some of our other partners. Thank you very much for listening, and that's everything from me.
Right. Yeah, thank you, Mike, for this great presentation. And in the interest of time, we will directly move on to our last and final speaker, Dave Everline, who is one of the lead scientists of the Cold Atom Laboratory, not only leading the work on several ground test bed, but basically, you know, Dave, if I may say so, being one of the initiators of this mission right from the start. So I had the pleasure to work with Dave when I joined JPL, so he prepared everything very nicely. And yeah, Dave, please, I may hand over to you for your presentation on the Cold Atom Lab.
Well, thank you, Markus, for the kind introduction. Thanks to everyone. I'm happy to be here. Tell you a little bit about the Cold Atom Lab. And basically, this is a system designed and built at Jet Propulsion Laboratory. It's sponsored by NASA. And I guess I'm going to run right to the punchline. And we are on a satellite that is a bit larger than some of these other CubeSats we've been talking about. I feel a little bit like we've cheated or something here, but I'm very happy that they started building up the ISS 20 plus years ago, and we had a home to go to set up this laboratory. So I'll just start with a little bit of background. I know some of the audience may not be as familiar with cold atom research, and then why microgravity is such a benefit to it. And even before I get too far into that, I just want to make sure we're all talking about the same or have the right thing in mind. When I refer to a cold atom or this kind of research, we're using dilute gases. So those are neutral atoms. We consider them generally, they're non-interacting. And in our case for Cal, we work primarily with rubidium, but there is also potassium enabled. So the idea is to be able to do some molecules and some other research also with potassium. You're going to hear mostly everything centered around rubidium today. That's the workhorse. So over the last 20 plus years, really almost 3 decades going back, it's been an area of research that has obviously thrived and done very well, as outlined by several Nobel Prizes scattered throughout, the 90s and early 2000. And really that's where, going back even into the 90s, a lot of these physicists realized that there is a benefit by going to space or going to a microgravity system. We put this effort into getting a sample of atoms very cold and very dense. Usually they become more useful for us as sensors or studying other physics if we then release them. And so they're then unconfined. And on the ground, we're limited usually by the size of our apparatus, because they'll either, well, number one, if we're not cold enough, they expand, they become dilute and you don't see them anymore, or the center of mass alone, they just fall and fall out of view or fall to the bottom of your system. And so the other side that I just mentioned was about temperature. One of the advantages of going to low gravity is that we can move to these very weak traps. And so by adiabatically expanding or decompressing into these weak traps, or even some other advanced techniques of kind of magnetic lensing and so forth, there are advantages to being without this asymmetric force that's always kind of, unfortunately, we're stuck with it, right? So a lot of systems over the years have been, there are techniques like atomic fountains. I have the kind of extreme case here of this 10-meter fountain in Stanford, lower left. We've got the approach of making a much bigger tower, famously the Bremen drop tower. We'll evacuate the entire chamber and then drop your entire experiment through it, or launch it and get maybe up to 9 seconds of free fall time. There are Einstein elevators. There are smaller ones. I know Bremen, or there's also an Einstein elevator being built. This can get us 4 seconds or so. And some more dramatic efforts, the sounding rockets that Mayas demonstrated. We've got parabolic flights. These are getting us to the tens of seconds and even minutes with Mayas. And so all of that said, one of the things that Cal managed to take advantage of is the fact that over, in the 90s and into the 2000s, they're working on the ISS. And so actually, this was the original slide, but then I did a little internet search and decided to put this as the top part here. So we're able to leverage the fact that they've built a laboratory basically in orbit. So we're in perpetual free fall. And we could make use of the fact that they basically build in these express racks. These are you can think of them as just our standard equipment racks. There's a very structured footprint, and we can build around this set of 8 lockers. Cal uses 5 of those 8. And it provides power, it provides water and air cooling. So there's a lot of difficulties and challenges already helped out by the fact that there's this facility there that's a short sleeve environment. We even have some personnel at our disposal, not too often, but they will do some install and do some repair and the replacement of upgrades and things. So I'll get into that a little bit later. All right, so let me keep clicking. All right. Am I in the full? I might not be in the full. There, is that bigger, or is that about the same
Yes,
view?
that's nice. No,
All right, sorry, I thought I was already in that mode.
Nope, no worries. We didn't want to interrupt.
Okay, so in particular, there's this express rack. This is, of course, just a CAD rendering. But we're occupying 5 lockers. We're taking up a quad locker, which is a set of 4, and that's our main science instrument. We also, sorry, I'm minimizing another thing that's in my way. We also have a 5th locker that's holding most of our power electronics, but it also holds some other components, including some optical. So let me skip over to, this is basically the quad locker itself, and semi-exploded view. The front panel is off, and some of these drawers are shown to have pulled forward. The main goal here in designing Cal was to make it modular, besides just sort of trying to pack a room-sized laboratory into a box. We want to make sure that it could work for up to a few years, with the idea being that some lasers might need replacement, or part of our specific plan, for example, the science module got removed and replaced with another module this past February. So I called out a few of some of these components in there, but our main CPU is in the lower left. That's actually not meant to be replaceable, although maybe with some extra work cut out for them, they could do that. The lasers and some other components that we decided are potentially only a couple years lifetime. They've actually so far been very impressive and held their own. We will be probably replacing some electronics in the coming year. So let me move on, but that science module is in the upper right, what I'll kind of draw your attention to, and that's going to be in this next slide. Basically, the science module is the vacuum chamber and all of its kind of rigidly mounted surrounding hardware. So that's going to include the outermost part of it is this 2-layer magnetic shielding. And then we've got a lot of the mechanical structure that's holding the free space optics that's being shown in to create our 2D MOT, our magneto-optical trap, and our 3D MOT. We also have, of course, the vacuum chamber in the middle of it, and there is water cooling and some thermal management. You see some thermal straps and things in there to help bring some of the heat out that the coils and these other dispensers and things kind of add to the system. So especially when you're in the with no convection in a microgravity environment, you need to address these kind of things. So on the far right, by the time we've kind of zoomed into the middle there, we see the CAD of the science cell. On the top is a two-chamber system. The source cell at the bottom has a slightly higher vacuum because that's where I should say it's a lower vacuum. It's a lower pressure, a higher pressure. And the dispensers reside at the bottom of that one. And yeah, here we are. The dispenser is kind of located at the bottom of this source cell, and we heat that by running current through it. It ends up creating we're in the sort of 10 to the minus 8, maybe up to 10 to the minus 7 at most. The aperture that you see at the top of the source cell is what differentially pumps and allows the upper part of the chamber to be at 10 to the minus 11 torr. And shown on that far lower left is just a picture of this two-dimensional MOT. So basically we've cooled along 2 directions, and that leaves this elongated cold beam, which is flowing up, goes through this aperture and loads this in the science cell a 3-dimensional MOT. And at the very top of the entire chamber is this atom chip that forms the ceiling. And this is where we load atoms to do the very tight magnetic traps and get evaporatively cooled. Okay, so just to kind of show a little bit of this internal structure, obviously this picture on the right, we have half of our shields off in order to take this picture, and sort of overlaid with it is this illustration to show you some of the beam pads. Again, 2D MOT located at the bottom. We do take advantage of a small push beam. This helps increase the atom flux of the beam that goes up to load this 3D MOT. The 3D MOT is made. These are all retroreflected beams. There's a third axis that's in and out of the page. And we have our sort of parallel to chip imaging along this y-axis. And that push beam also serves as an imaging axis through the chip. So it gives us an orthogonal view if we use it with lower attenuation. And so this just sort of shows you an example of that type of imaging. We're doing absorptive imaging where we flash 2 very short pulses. One is on resonance with the atoms. The second pulse is off resonance. Same down here with the parallel chip. And it's so hard to see here, but in this little region of interest, this little zoomed in yellow box, we end up seeing our processed image. The false color here, red, is the most dense. And as we fade to black, that's no atoms. And so everything we get about the cold atom position and momentum and its spatial distribution, it all comes from these images. There's really we get other telemetry down from Cal about how the temperatures are on different lasers and the currents, but all the science data comes from this very simple set of images. In order to get there and take those images, basically we load into what has been coined an atom chip. This allows us to get a lot of, without using hefty amounts of current, kind of on the order of amps or less even, we can make very tight magnetic traps very close to the surface of a chip. So this is a semiconductor kind of style device. It's silicon with copper traces patterned onto it. These are on the order of these are about 100 microns wide, 10 microns tall. And by running in the Z current, for example, here, this zigzag, by running about 3 amps and under an amp in this dimple, we can make a very tight trap, basically in all directions. About in our case, we're working with about 1 kilohertz trap frequencies. There's one direction that's weaker than the rest. That's what this dimple helps provide a little bit tighter along that axis. And this is where a very sort of standard approach in the field is to apply an RF. It's coined an RF knife. So this radio frequency is resonant with atoms when they're at certain magnetic fields. And by ramping that from high to low at the right rate, you can basically discard all of your hottest atoms, or you keep discarding the hottest atoms and you're left with colder and colder samples. All right. So on to some of the results. I will first just jump through and say we have, on a daily basis, basically for the last 2 years, been producing BECs. This is an example of sort of a run that I was just describing as we cut lower and lower with RF. This is a sort of a thermal gas here on the far left. As we cut deeper into that system and make the atoms colder and more dense, we see this striking feature pop up, which is the BEC, kind of the core of that cloud. And on the ground, that's typically what we get. And so these 2 pictures on the far left are taken with the same exact parameters, the same table that was prepared on the ground, making consistent BECs. We fired off that same sequence, and we got very, well, in some ways, very similar results. Our BEC, we still see this very dense core and very cold, but we were surprised to see about 2 to 3 times more atoms surrounding this cloud. And so this is the same picture, larger view. If we step through, you could see that by decompressing and changing our magnetic fields, we can pull all the magnetically sensitive atoms away from this halo cloud of insensitive atoms that, because in gravity there's no force on them generally, they tend to hover around. They actually also, the timescales we've seen, they seem to be not just hovering around, but actually weakly confined by the quadratic Zeeman force. So once we apply some Stern-Gerlach, we can separate out these different states. This is the primary state we were planning to work with. You get some little residual 2-1s, but then this halo cloud indeed stays there. We can apply larger fields, it all still follows, and we can apply even larger fields for longer time, and we actually can move around this generally considered non-magnetic state, but it, like I said, there's a quadratic Zeeman effect that allows us to move it or even trap it. So with that control, we were able to move to not only making BECs, but doing some very long adiabatic like decompressions of the cloud. The OD here is very saturated in order to be able to keep the same OD and see these clouds way out here. But I'll just say that by the time we go to about 300 milliseconds, all of the thermal, otherwise thermal surrounding gas and this halo cloud have now dissipated and very dilute and invisible. But this almost pure BEC cloud is basically drifting away from a chip. The chip is at the bottom here, and Z-axis moving away is going up. And at about 1 second, we can still make barely make out, but we can make out this cloud. So it's very important. In our case, we were trying to, part of the protocol there is to get very little drift. So they're not, this is showing they're not getting accelerated as they move away. They just have some initial push when they started. And the other thing we can look out for, especially as we move to long times, is how cold they are, or basically how fast they're spreading out. And we can confirm that they're sub nanokelvin. This is each axis is corresponding to about 200 and 700 picokelvin. Okay, so that was all very exciting, and we basically carried out a 1.5 years of science. In the meantime, we built up a third science module. There was one that remained on the ground. Science module 2 was in space, and we made number 3, which has an atom interferometer on it. And so I won't spend long, but we can, if you have questions later, we can talk about it. There's basically a Bragg beam that is retroreflected along the science cell, and it for a very short time span sort of demonstration, we've now shown that we can indeed put them in superposition of these momentum states, and by changing the phase of our Bragg beam, demonstrate fully this atom interferometer. And so this was pretty exciting to us this spring. This isn't published yet, but it's in work to get our longer and longer interrogation time. And I'll also say over the last couple of years, there's been a variety of different PIs and co-Is working on a range of studies. And there's also a couple groups that are ground studies and working towards future work in the microgravity field. So with that, I think I mostly chewed up all the time, but I do want to say thank you to everyone listening here, and also call out that between the sponsors at NASA, I mean, working with some amazing astronauts to do these installations and changes on while they're floating around in space. There's so many companies that contributed. Cal was considered a Class D mission, which is a little bit streamlined in terms of a budget and schedule. And we really did rely on a lot of these commercial products. And that's where, kind of going back to it, it is about starting small. There's a lot of components and sort of decades of development that really led to us being able to build this system. So I'll end there, and thank you, everyone.
All right. Yeah, thank you, Dave, very much for your presentation, and yeah, especially for being here live and present, giving this talk. I mean, for you in the US, it's really it's in the middle of the night, so we really appreciate your energy and your willingness to present these results. I think they are very exciting, especially the atom interferometer results. So I'm already very much interested in. So we do not want to keep you up for so long. We have had 3 speakers in the second session, and now we should go in the Q&A discussion. And I already have one question in the chat, which is directed to Michael. So Atta is asking, what is the level of the magnetic field susceptibility of the atom interferometers, and what are the shielding solutions currently being used? I think probably being used in CASPA, and maybe some general comment on the shielding to actually being able to measure something useful in space.
Yeah, thanks. Thanks very much for the question. So actually, the magnetic field enters in a few ways, or background magnetic field enters in a few ways. So the steps one takes to try and avoid that is we use a non-sensitive magnetic sublevel for our atom interferometer, but that still sees second-order Zeeman shifts, and actually even shifts at the kind of milligauss level would be very relevant there. If you're looking for a very sensitive performance. But it's not just that, and they actually can change position of the cloud, for example, which can give systematic shifts in your interferometer as well. So if your cloud is changing position before it's launched, that, depending on the sensitivity requirements, may not be a problem, but if it's moving around inside the beams, it will change the dephasing effects. It may change the trajectory of the cloud when it comes out of the trap, for example. So it's a very serious issue. There are two main ways that people are really looking at kind of shielding the magnetic fields. One is with passive shields, such as mu metal, for example, and other materials. And that's, it's very effective for low frequency fields, but it's very heavy if you want a very good shielding factor. And it also is quite subject to issues such as being knocked or heated can cause issues with changing how permeable it is. The other people are using is active shielding, so using other fields to cancel out magnetic fields, and that can be very effective as well. But that depends a little bit on the form of the interferometer that you're going to use, and if there's some kind of trajectory involved, you may have to shield that whole trajectory or so. And the last thing people are doing is, of course, thinking about other atoms which need less shielding factor, such as strontium, for example, because then you would be using an atom with no ground state structure. I hope that helps answer the question.
Mm-hmm. Yeah, thank you, Michael. So more questions. So there's another one by Leonard. What are the main concerns to ensure that the laser source and system work long-term in space? So,
well, I think there's a lot. I mean, we have the classical problems of the lifetime of each component needing to work for the duration of the mission, for example. That's the first step which one would need, because if we were really going onto a small satellite, there'd be no chance for any operator intervention, and if something failed, it would mean your whole sensor was gone. So those are very important, and the kind of mission lengths one might be thinking about would be years type duration. But then if we think about the space environments, a particular concern with the fibered systems is radiation hardness, and that of course affects all of the system. But fibers, certainly at certain wavelengths, can be a rather big problem there for a long-term mission. So looking at how one can either use fibers that are more radiation hard or shield in some way is something that people think about. And that's another push towards perhaps some free space lasers.
Okay, thank you. So maybe also, if I may add, we're speaking about getting something to space, and here's somebody who actually operates something in space. So Dave, what from your perspective over the last years, what are the most critical steps in the design of the system, or what have they been, and what are you finding out, what probably needs to be replaced more frequently than envisioned? And on top of this, Alex also asked if you have seen any radiation effects on your system during Cal, especially also with regard to the electronics.
Yeah. So in particular, I'd say Cal does benefit from the fact that it's inside the ISS. So when it comes to something like radiation, it is fairly benign environment. I mean, they have to have humans living up there too, so they make sure it's yeah, anyway, it's a reasonable radiation environment. But there have been, if anything, where we've seen it the most is with Cal. We've also sent up a kit of other tools that we use. So for example, the astronauts use a little fiber viewer. So in order, before they're mating or demating optical fibers, they had to do some interlocker between our two lockers, some fibers. We easily see that on that little commercial product that we had bought and sent up, now we're starting to lose, we've sent up another one because they're losing pixels that are now hot or dead pixels. We have had a number of anomalies on Cal over the last couple of years, and usually radiation effects makes it onto our, we call this a fishbone a lot of times, but basically our list of potential culprits. We may be seeing some things with our software, our computer. We have a solid state drive. It's not clear if there's been some more instabilities over time because of this kind of thing. One of the, I mean, just to maybe answer your first part of it, Marcus, one of the things we ran into very early on in the first few months is our our spectroscopy signal was changing pretty dramatically. The first month or so, it was fine. We were still locking the way we always would with the error signals. We had some automated lock sequence, so we didn't need to look at it. We thought we didn't. It turned out there's actually some background helium levels on the ISS, and this was permeating through a few silica, small cell, very thin walls because it's a small cell. And so this is one of those areas that without that being actively pumped on, this became a there's actually some collision effects that make a difference for that kind of for rubidium spectroscopy. We basically see the spectroscopy change over the course of weeks. Now, in a full space environment, maybe there's less concern about that. But anytime you go to these new environments, there's some sometimes there's these other gotchas, whether it's thermal or what atmosphere you're in. So that's
all right,
that was one that rose quickly to be almost a showstopper for us. So.
Okay, yeah, luckily it wasn't a showstopper, as I guessed. Yeah, Mike is also pointing in direction of what have been the main risks. So he's asking you, like, what was the thing which kept the people awake the night before the launch?
Oh God.
And also the biggest risk on technology. I mean, where would you point towards?
I'll say that what kept me we had a lot of we had a fair amount of uncertainty about our fiber coupling, like basically fiber to fiber matings, that usually I would have, with some experience on the ground, said it's not a problem, or it wouldn't be a problem. You pick them out and they should couple. It seemed like more, I don't know if it has to do with that mate and demate count or what, but we had a few that were very troublesome in the final days leading up to before launch. So after having gone through that and gotten the coupling just great and everything's torqued in, I still had a lot of concerns that after the launch, and I did get to go see the launch too. So after sort of experiencing this loud and violent thing, I definitely was keeping me up that, are we really going to have all of same? I mean, it's not only maybe the fiber to fibers, but free space. These are pigtailed devices. So is our power going to stay? And I think fortunately we had pretty good luck. We did have some headaches with some of the interlocker fibers that the astronauts needed to install, but they learned the right methods and were able to get it done. Obviously, if it's a hands-off system, I actually made me feel better about that. Some of it, because we knew they were going to be interfacing with it, it made us pretty concerned. There's so many there's so many other things that kept me awake, but that was one that stood out.
I mean, you're awake right now, right?
Yeah,
even without worrying too much. Okay. Yeah, if there are more questions, please put them in the chat or raise your hand. Other than that, I have, I'm of course interested in asking about the atom interferometry results so far, or, the sequences you're running there. Can you comment a little bit on interrogation time and, what's limiting you towards going to longer times?
Sure. So coming out of the gate, and this is Jason Williams is really kind of leading our effort on the JPL side, but there's there's a number of PIs that are actually all collaborating with this effort right now for the atom interferometer. Right now, I mean, for instance, those results I'm going to say are on the single millisecond timescales. Nothing too dramatic. It's just to get the shots that I was showing in the earlier presentation. I think things are growing out into the tens, and the goal would be at least getting into kind of hundreds of milliseconds interrogation time. The limit right now, or at least starting out, was where the atoms were positioned within the Bragg beam. The beam is only about a millimeter, in size, and there was enough drift, and they have enough drift or movement out of the beam that by the time a few milliseconds went by, not completely out, but out far enough that that signal is getting ruined. So there's been a lot of, there's been energy put into getting them into, number one, in an efficient way, getting them into that non-magnetic state. So there's not this gradient or other accelerations happening. And also getting the right momentum. You need them to be moving down away from the chip at a slow pace so that you can interrogate them with the Bragg beam, and you want them only moving slightly away and not side to side. So that's been really, so far, that's been the main challenge, to go from singles of milliseconds to hopefully soon it'll be hundreds of milliseconds. There's loftier goals for that AI system, but I think for the near future, that's kind of the timescales that we're talking about.
Okay, great, thanks. Any further questions from the audience? Let me check the chat. Somebody raising the hand. Okay, then maybe, I ask also another question, maybe to Aaron. What do you think now, seeing all this developments also related to the stuff you've been presenting? How small do you think you can get with such a reference module in the future, and what steps do we need to undertake?
So I think a major advance technology-wise, which is promising to reduce the size even further, is the development of MEMS cells. So wafer cells which are really compact, based on silicon wafers and anodized glass. And I think if you get into control with magnetic fields, right, if you place an isolator, then this of course restrains the size that you can pack everything together. But if you can solve this issue with back reflections and so on, I think that a butterfly package is actually achievable for these modules. However, as it seems that many people already achieved a lot with commercial systems, I think that this is still a long road to get unto this point. And as these are research missions, you will need a significant commercial push in this field. So I hope that the commercial environment will foster further development into this direction. So compactification can also only thrive if there's enough demand, I feel.
Okay, thanks. And then maybe one question by Dave to you both, Aaron and Michael. He would like to know what technology is the most challenging or poses the most risk in your systems. So yeah, maybe Aaron, you can start, and then we hand over to Mike.
Yeah, so there are different options how you can improve the performance of these systems. So as I said in the introduction of my talk, that you can go for, of course, atomic sensors and so on, but you could also go for atomic clocks. And for atomic clocks, there are major systems in reducing the size of vacuum systems, for example. So development into the direction of metal printing or 3D printing could be beneficial also for the arrangement of optics. But I think, yeah, reduction of the vacuum technology, optical alignment systems. So we use just benches, but if you can use 3D space for optical alignment, this would be nice. So other major challenges, yeah, if you look into photonic integration, so if you at some point hit the edge of reducing to chip scale levels, then of course you have a lot of issues with the materials that you want to integrate, be it lasers or some optical parts. Yes.
Mm-hmm. Thank you. Yeah, passing on to Mike.
I think if you could have one magic pill, it would certainly be the laser. If you could just have a laser that works very well, you've got, does everything you need and never fails, then you're in easy streets, I think. So for us, I think we have some concepts for how we could fit a laser system into something quite compact, but the number of functions it has to perform is quite large, and being able to do all of those to specification, that's quite challenging. So being able to have a laser system that can perform all of the different cooling, atom interferometry, manipulation steps, but still be resilient against drift over the lifetime of the mission, or have a way of removing drift from its performance. That's, I think, quite challenging. Probably the biggest risk.
Okay, yeah, thanking you. We all take this back as homework, and with this, I would like to close this part's Q&A. I would like to thank the speakers again, the participants for the question in this session, and I hand over for the closing work back to Alex.
Thanks, Markus, and actually, thanks everyone. I would like to, first of all, give my heartfelt thanks to all the speakers for sharing us, the latest results that they have, and also to David, who's actually in the US, for staying up to share with us, even some of these unpublished results. That was actually very exciting. And for the audience, I hope you guys enjoyed the talks as much as I did. I found it actually, I think although this is our first virtual session, Markus, I thought that this was the best edition we've had so far.
Yes.
And so I think this is because of our selection of speakers and also the participation from the audience. So I'd like to thank everyone again, and I hope you all have a great weekend ahead. And we'll meet again at the next QTX edition next year, and hopefully in person this time. Markus.
No, I mean, nothing to add. I also think that there was one of the greatest QTXs we had. Everybody starts small. So thanks again, everybody, also from my side. Yeah, and I have nothing more to add rather than wishing you a good Friday. You start or end of Friday. I'm not sure in the time zones. It's all messed up, but in a positive way. So yeah, thanks a lot. Thanks to all the speakers. And yeah, with that, I think we can close our small conference.
Right. Thank you, everyone.
Thank you.
Thank
Good
you very
night.
much.
Thank you. Goodbye.
Thank you.